welcome back. So in this video, I'll be doing this particular limit. So basically, you're calculating the limit as x tends to infinite, log x to power b divided by x to power a is 0. So to prove this limit, I'm going to do some inequalities. I'm going to do certain, a little bit of analysis. So let's just dive in to see what the proof is. So the proof is, what I'm going to do is I'm going to pick a variable t, and t is bigger than or equal to 1. So why I'm going to do this is because I want t to the power minus 1 to be less than or equal to t to the power some number, let's say c minus 1. Okay, so where c is positive, right? This holds, definitely this holds, because when you choose t to be bigger than or equal to 1, what you have is t to the power minus 1, and this term is basically t to the power c multiplied by t to the power minus 1. So basically you're multiplying t to the power minus 1 with some positive number t to the power c, right? So basically then you definitely have this greater than or equal to sign because you're multiplying by a positive number, right? So this is true, right? So this implies this, right? Okay, so what is the motivation for this? So basically what I want to have is I'm going to expand logarithm, so log of x, in terms of an integral. So integral 1 to x 1 by t dt, right? This is log x. This follows because we know that integral 1 by t dt is nothing but log of t, and when you have limits 1 and x, you just evaluate it 1 and x, so this is log x minus log 1, right? So you have this, and log 1 is 0, so definitely this is log x, right? So log x can be written in form of this particular integral, right? Okay, so as you can see here, this is t to the power minus 1. Basically 1 by t is t to the power minus 1. And so when you have this kind of an inequality, I can make an estimate for log x, right? So log x, which is basically this integral 1 to x 1 by t dt, this is less than or equal to integral t to the power c minus 1 dt 1 to x, right? So basically I'm using this particular inequality to make this estimate. So let's expand the right hand side here. So this is basically you do the integral. So this integral is t to the power c minus 1 plus 1 divided by c minus 1 plus 1. So basically you're calculating the antiderivative and evaluate at the limits 1 and x. So this is x to the power c minus 1 divided by c, right? Okay, so what do we have here? So log x is less than or equal to x to the power c minus 1 divided by c. Well, I can also say that this is less than or equal to x to the power c divided by c. Okay. Okay, so in this case, I'm also assuming that the x is bigger than or equal to 1, right? So that assumption also goes in. So I can, because x is bigger than or equal to 1, right? So log of x is bigger than or equal to 0, right? So it's bigger, it's bigger than 0 if you have x bigger than 1. If you have equality if x is 1. So I can definitely say this is bigger than or equal to 0. Okay, so this is a kind of an estimate for log x, right, for some positive number c. So basically if you go back a little bit, I said that c is positive, right? So c is just some number which is positive. So using that, what I can do here is that I can raise this to the power b both sides. So what happens is this is less than or equal to log x to the power b, less than or equal to x to the power c divided by c to the power b, and then you divide by x to the power a both sides. So this is x to the power a. So basically, you are trying to get an estimate for this particular term here, which is basically the limit that we want to estimate, right? So we want to estimate the limit of log x to the power b divided by x to the power a. So you have this here. Now, right hand side can be simplified a little bit more. So c times b minus a divided by c to the power b, right? So you multiply c and b, and then you're dividing by x to the power a, so that becomes x to the power c times b minus a, right? So you have this. Okay, so now you can evaluate the limits, right? So what I'm going to do is I'm going to take the limit of this particular function here. But before doing that, let's try to fix the value of c. So c is some random number bigger than 0 for now, but I'm going to pick a specific one, let's say 1 by 2 a by b, right? I can do this because this is another positive number. And when you make that particular choice of c, what you have is that 0 bigger than or equal to log x to the power b divided by x to the power a is less than or equal to, basically you just substitute 1/2 a by b and then multiply by b minus a divided by 1/2 a by b to the power b, right? So now what happens is that the right hand side becomes, so let's just write this down again, x to the power a, and this is less than or equal to x to the power b get cancelled, and that's a by 2 minus a divided by 1/2 a by b to the power b, right? So this is x to the power minus a by 2 divided by this particular term, 1/2 a by b to the power b. Now, what happens when you calculate the limit as x tends to infinite, right? So when you take the limit as x tends to infinite of x to the power minus a by 2, this goes to 0, right? This goes to 0 because this is of the form 1 by x, kind of like this form, right? 1 by x. So when x becomes bigger or x tends to infinite, this tends to 0, right? So that's the same case when you have x raised to a by 2 or any such number. As x tends to infinite, this ratio tends to 0. So this particular limit goes to 0, right? This is a constant, so it stays 0 for the whole time, because this is you can think of this as a constant function. So this particular limit, we know the limit x tends to infinite of this 0 is basically 0 again. So left hand side and right hand side goes to 0 when you take the limit x tends to infinite. From this you can say that the limit of this particular term is again 0, right? So this is limit x tends to infinite log x to power b divided by x to the power a is 0, right? Because the right hand side tends to 0 and left hand side is already 0. So what you can conclude is that the middle term, right, the middle term, as you take x to infinite, this goes to 0. So this is what you have here, right? So that's how you prove this particular limit, which is very interesting. Well, actually, if you can prove this particular limit, you can prove another limit. Let me just write it down. So limit x tends to infinite x to the power b divided by e to the power ax is again 0, right? So you can prove this as well. So how do we do this? So let's look at this ratio x to the power b e to the power ax. Let's make this substitution. Let's say e to the power x is t, right? So what you have now is that log t is x. So instead of x, I can just plug in log t to the power b, and we know that e to the power x is t, so t to the power a. Well, this is of this particular form here, right? The only difference is instead of x, this is variable t, but that's perfectly okay here, because when you take x to infinite, your t also goes to infinite, right? So when you have x goes to plus infinite, t goes to plus infinite, right? Okay, so this should be plus infinite. That's what I meant, the whole for the whole part, like hold the so it should be infinite, right? Right, so that should be plus infinite. Okay, right, so we have this. Now we know that when the limit as t tends to plus infinite is 0, so this particular limit, so limit as x tends to plus infinite, x to the power b e to the power ax is basically when you take x to infinite, t goes to plus infinite, so log t to the power b divided by t to the power a, this is 0, right? The 0 is follows from here, so basically this limit is again 0, right? Okay, so that's how you prove this particular limit as well. You get it from this one. Okay, so I hope you followed all the steps that I did, and yeah, so I'll see you next time. Take care.